AI some alpha opacities. And this trick lets you, what this is really letting you do is it's really letting you correct for changing opacity along the ray so that you can take samples anywhere along the ray, and if you take 4 samples along the ray or 200 samples along the ray, you're not going to have wildly different non-corrected opacity based on how many samples you've taken. So that's what this exponential is really letting you do. It's really correcting for the attenuation that you get from taking lots and lots of samples. Let's see. So this is basically letting you do the same thing for color values as opposed to just opacity values. And the only thing that changes here is that before you would actually have just these opacity values A, but when you have the color values, you actually, the color comes out front, and you multiply multiply these opacity values by the color value. So that's sort of a way of weighing the colors that are coming out of these alpha blended samples. And then you're basically going to do a sum of all of these products. And this is really, this looks a little bit confusing, but it's actually the same underlying equation as the alpha blending operator that we had before, where we have colors multiplied by 1 minus alpha, just recursively. So we're doing this over and over again. We have a sum of products, and this is really the discrete equivalent of this continuous equation. Now, this has nothing to do with classification. There's no transfer function or color map here yet. So far, all we have are opacity values and color values. So the color values, for example, could be coming straight out of the volume. But this is how you would just alpha blend together a bunch of samples along an array and get a single color value out of it. And yeah, again, if you look at this, this is the exact same blending operation that we had before. And we were just doing this sum of products recursively, which looks like doing this C prime equals C plus 1 minus A times C prime of the previous sample. And it turns out that there are actually 2 ways you can do this. You can do this either back to front, so starting at the back of the volume and integrating frontwards, which is a little bit simpler, and that's actually what we just derived in these slides. Or you can do it front to back, which is a little bit more confusing, but looks like the same thing. But it's really the same thing. And the advantage of doing front to back is very often you would, especially in the raycasting case, you would generate a pixel at the front of the eye, and you would want to go towards the back. And very often if you hit something in the middle and you've determined your opacity is opaque enough, you can actually stop in the middle of the scene and not do any more work. And this saves you a lot of effort, a lot of computational effort. And that's what we call early termination. It's very, very useful in making your rendering software faster. So that's front to back compositing. Yeah, and again, we stop the calculation when this alpha I is almost 1. In practice, it'll be slightly less than 1. It'll be like 1 minus 1 e negative 6, but that will be usually enough to make the difference and make your code much faster than it otherwise would be. So in summary, there are 2 ways of doing, so this is what we refer to as the emission absorption model, where we have no scattering, just emission and absorption. The absorption is what causes the ray opacity to attenuate or diminish as you go through the volume. And the emission is really just the concept that each voxel value has some emitted light component, some color that you're blending together. And that might be more complicated than it's worth. So I will just show you a simple for loop that summarizes all of that in about, looks like 12 lines of code, maybe 16 lines of code. Basically, you have a big for loop. You start out with color and alpha at 0, and then for each, you find your front and back samples along the array, and for each sample, you're going to get the value of the volume at that sample, so that's that sample's 3D texture. Then you're going to classify that, and I'll talk about that in the rest of the lecture, how we actually do this classification, how we go from a value to a color and opacity. Then I'll talk, and then you, optionally, if you want it, you do lighting. So you have this shade function that applies the Phong or the diffuse model. And then you have this the blend operator, and that's using the blend code that we had before. Then you increment your sample, which is using that step size, that delta t concept we had before. And then you determine if you can early terminate. So here I have a really, really aggressive early termination criteria. So it will basically terminate at the instant anything is even remotely opaque, but that's just an exaggerated example to give you an idea of what early termination looks like. And this is just, this is an example raycasting code. So actually, I will take this moment to give a little demo of that. So this is some even simpler code than ParaView. And the reason I'm mentioning this is that if anybody wants to use this code and wants some simple GLSL shader code that's easy to start off with, or at least a little bit easier than digging into ParaView with Osprey, or even something like ImageViz 3D. There's a tarball that I have on my website that came from code I used in my Viz 09 paper, and that kept on being used in several other papers that went into this nanovol molecular software. And that basically does this. So here we have, and it's amazing, this was amazingly slow, like 1 frame per second on a discrete GPU back when I wrote the paper. And now it's a little less slow in my laptop. But still, yeah, there we go. So here we have a transfer function editor, and so these peaks that you see here, so this axis, the vertical axis, is opacity, and then we have a bunch of control points that represent color. And if you move these around, they are more or less specifying the mapping from of color and opacity to sample value. And this is what we refer to as a 1D transfer function. It's one-dimensional because you're only really looking at one axis, the value along the value of the domain along this x-axis of the transfer function. Here, let's make it a little bit faster. And if you can lower the number of samples along the array like this, and you can see that it becomes very coarse, but also very, very fast. And you can also increase the number of samples along the array. And if you do that, it becomes very accurate. You can see we're sort of converging to a correct image, but it also gets very slow. And the fancy math with the exponential function, what that's really doing is it's allowing us to have more or less the same visual result and not wildly biased color and opacity depending on how many samples we take. So I left the link to that tarball in the slides. Anybody who wants to grab it, feel free. So now I'll talk about transfer functions, how we go from color and opacity to actual values of samples. So going back to the emission and absorption model we had in the previous slides, supposing we have the emission values, so emission is really color, and absorption values, so absorption, you can think of this as sort of the opacity. And how are we going to go from a scalar value S to an RGB emission value and an alpha absorption value? Trying to figure out what this is. Oh yeah. Oh, so what this is showing is that there are multiple ways you can do this, and depending on what values you choose, you can have a low alpha value for a lot of these samples, and you can segment out a lot of this. So if you do nothing else and you have no alpha, you just get this sort of pseudo-color plot where everything looks like a black box. And if you classify just opacity, just alpha, you can actually get this sort of maximum intensity projection type image which is a little bit like what you'd see coming out of an X-ray. And you can also change this opacity to sort of highlight features of interest. So if you go back to the example I had with that zebrafish microscopy data, when I was doing the live demo, that's more or less what the peaks are doing. When you have a peak, it sort of accentuates a feature, kind of like an isosurface that you'd want to look at. So you're looking at maybe one value or another. So yeah, maybe this is yeah, let's do this. So this blue peak right here. So if I diminish this, then it's going to, that feature will sort of disappear. And it's the same principle in this slide. Yeah, here we go. And then lastly, once you have this sort of classification, you can actually apply color. So you can color features you're interested in that are deeper than the data set with something really bright, for example, and things that are closer to you that you're less interested in, that, for example, wrap around the volume, you can make those something grayscale. That's a very common technique in 1D transfer function classification. So transfer functions make volume data visible by mapping these data values to optical properties. So yeah, you're starting with a block of volume data and you don't know what's inside it, and you're going to end up with a volume rendering that looks, if not like a surface, then something your eye can immediately grasp the shape of. So the simple example is usually to map the data value f to some colored opacity, and once you do exactly what the volume rendering algorithm in the previous slides did and blend everything together, you'll end up with, and have shading as well, you'll end up with an image like this. So yeah, the general idea in all of volume rendering is you start out with domain space, and then you have these data values that are somehow normalized, maybe according to some histogram equalization, but that's not even necessary. And then you're going to use the transfer function to map from that to color and opacity. And the idea is that the range of the transfer function closely maps a sensible range for the domain. So you're going to base your transfer function on, for example, a histogram of values in the domain, and that's sort of how you will control which features you put where. Now the challenge is that coming up with a good transfer function can be surprisingly hard. And even minute changes to the transfer function can have immediate and dramatic impacts to the actual model you see. And in some ways this is no different from what you'll see from isosurfaces in so not this Thursday's, but next Tuesday's lecture. Except the problem is in fact harder because, first of all, everything you do is slower, there's a lot more occlusion, everything is overlapping everything else, and you have both color and opacity at each value to deal with. So one way you can look at this is if you have, so very often these volume data sets will have sort of like an onion-like behavior where you'll have low values on the outside and then high values on the inside, or vice versa. And your job is sort of to assign different material properties to layers of the onion to make them stick out. And this is exactly what I was doing in my little live demo with the zebrafish data set. And this is exactly what you're doing here, where you have a peak that, and one peak shows one material, another peak will get mapped to another material, and then a third peak would be another one. And the way you would actually decide where to put these peaks is based off of a histogram with respect to the value of your scalar field. This is kind of a rule of thumb. There are many problems with this, but this is more or less how you would design a one-dimensional transfer function. So your histogram, for example, if you took a histogram over your entire volume data set and you plotted it here, and you had the transfer function on top of it, you can sort of see these gray bars here. It's not a perfect indicator of where you want to put features, but in some cases it will tell you where not to put features. So for example, if you see an enormous mass of data that shows up in a certain range, very often, ironically, this is not that interesting because it sort of tells you this is where the bulk of similar and uninteresting values in the data set, or just simply noise, exists. Whereas if you end up having interesting sort of mini peaks further on in the data set, these are very often more interesting distributions that indicate, okay, there's a hump of data values that are in this range. Maybe we want to put a feature here using the transfer function editor. But after, I want to say, at least 20 years, probably more, no, 96, yeah, roughly 20 years, maybe 25 years of literature on how to automate transfer function design, no one has yet come up with a comprehensive way of doing it, or at least a way that eliminates all of the problems of how do you just eliminate the noise and the background data. So here's some very, very simple examples of what happens if you have a step function versus a ramp. Here's, again, some other examples of the step and ramp, and then color mapping the red, green, and blue channels. Some transfer function editors have this, where you have opacity on one axis and then red, green, and blue as separate axes. I'd say the more recent ones, like the pair view editor, the visit editor, the example that I showed you for Nanovol, those are all what we refer to as associated values, where you have a single graph that really is a function of opacity, and the opacity values map directly to color values. And this, I think, makes life quite a bit easier at the risk of sacrificing a little bit of flexibility in how you generate a 1D transfer function. But this is basically the idea of how you'd classify a synthetic spherical blob using a 1D transfer function. Now, this seems fairly intuitive up until this point, but we have some problems with 1D transfer functions. And very often we're interested in finding edge features when we don't really know where the edge is. And in image processing applications, there are very, very simple ways of doing this. But in volume rendering, I mean, there are equivalents, but you don't really want to apply those equivalents in an offline fashion. So very often what we're trying to do is we're trying to design a transfer function that lets us find the edge more or less automatically. And if we have something really nasty like this big blocky step, we'll have a very, very sharp edge. And if we have something like the ramp, we'll have sort of a smooth edge. So here what you can see is we're actually, we can sort of come up with good representations of edges using 1D transfer functions, but you have a lot of guesswork in actually doing that. So it would be useful to actually come up with techniques that show you where the edges are and how the gradients of the data themselves behave without you having to go through the guesswork of finding them. So that's, I'd say, the biggest challenge with 1D transfer functions. There's a lot of guesswork. You can sort of go through the entire data set, scan through it, look at the histogram, and get a sense of where not to place your features, but there's no one right way of generating a 1D transfer function. In the general case, and there's also not a lot to go off of when you look at the histogram either. So in a sense, all you can sort of do with 1D classification is run blind until you find something you like and claim that this is more or less interesting with respect to your volume data set. So in addition, there's some problems with how do you apply this to multidimensional data, multi-field data. I'm not even going to get into that too much today, but in short, I think the big challenge with 1D transfer functions is that you can't just look at the histogram or look at the data set and immediately know what to do. So actually, before I go into this, I think I will kind of conduct a bit of an experiment. So, yeah. Suppose you have a medical volume data set. What are some of the things that you would want to do if you wanted to design a good transfer function for that data set? And suppose you have software that is more or less going to do whatever you want. It has a 1D transfer function editor, you have a histogram. What's the first thing you would do?
See the tissue?
Sure. So the histogram, for example, will tell you where the tissue. That's true. So for example, the histogram tells you have lumps in a few different places, and there's a big lump on the outside, kind of like this. Okay. Do you want to look at the first big lump of data? Or do you want to start to look at the smaller lumps and poke through them until you find something interesting? I think you want to, yeah. Basically, you want to. So the way I've always looked at 1D classification is if you don't have any better ideas, you load the data set, you apply something like a standard red, green, blue ramp, and you're going to see this big, messy blob, a smooth ramp from red to green to blue. And the first thing that I would usually do, so maybe I can even bring up an example. Let's look at a nice, easy volume data set like heptane. Okay. There we go. A quintessential 1D transfer function, blue, green, red data set. And this is a really, really easy data set to classify because there's a lot of empty space that gets mapped to essentially opacity 0, and that's the white stuff you see around the heptane plume. And then as you get higher value, you end up getting features that are first blue, then green, then red, and red is going to be the highest opacity. Now, I guess as an example, if you had something like the CT head data set and you were looking at the histogram, you would very often have a big, messy blob of histogram values here. And what Alex was talking about with the tissue, you'd very often have little lumps scattered across the range later on that correspond to tissue or bone or various components that you want to see. And that's what you would do generally for a medical data set. And actually, I'm going to go into a more detailed example with 2D classification for that. But generally, for 1D classification, for a really clean volume data set like this, where your value goes from low to high, the first thing that I would usually do is just have a standard transfer function like this to get a sense of where everything lives. And then, for example, if I wanted to look at a certain ISO value, I can add a feature like this. Or you can add another feature like this. And you can sort of use these values to tease out more general shape. And you can add in lighting, for example. And I guess it makes a little bit less sense for continuum data than it does for medical data. In medical data, you really want to see specific features that correspond to specific densities from your CT scan or MRI. But in continuum data, you might actually have similar things too. For example, there might be a temperature that is that's sort of average, or that corresponds to the average temperature of the simulation, and you might want to ISO value that. So you can sort of do the same things in a volume renderer that you would with an isosurfacing or contouring approach. But yeah, that's more or less how you design a 1D transfer function. Is avoid the bulk of noisy and empty space on the outside, and sort of work your way from outside in, is how I would think of it. So now we're going to talk about, so how we do it. The approaches to transfer function design. One is trial and error, which is more or less what I went over just now. I mean, I call it work from the outside in, but that's about the most process I can provide for it. But that said, people like Joe Inslee at Argonne, Will Schroeder, and Lisa Avila, I mean, they've made some amazing transfer functions just by doing this. I mean, same thing with this zebrafish microscopy data. It took a long time to generate this transfer function, but once it's there, you have something that looks very nice and sort of captures the features you want to see. For example, axons, dendrites, in cosmology, filaments, for example, or halos. So the sort of image-centric way of designing transfer functions, there are lots of options here. I mean, there's probably a good 2 to 3 decades worth of literature on semi-automatic ways of specifying transfer functions. There was a genetic algorithms paper from Viz 96. There was, actually I'm not familiar with the SIGGRAPH 97 design galleries paper. I should actually go read that. If you look at, I'd say Viz in the last several years, I've seen a lot of papers on how to apply statistical methods, Gaussian distributions to sort of analyze features and turn them into 1D transfer functions, and then sort of reverse engineer what the best transfer function is. And actually, I'd say these are, and then finally you have this data-centric approach. Maybe those are more like the Viz techniques that I was referring to. So here you have techniques like contour trees, the contour spectrum, techniques that are really derived from the topology literature, and that sort of give you an idea of how to analyze the data set, especially the range of the data set, and sort of build something like a histogram but with more actual structure to it. And I'll actually talk about that in next Tuesday's lecture, as well as talking about isosurfaces. I'll go over topology and how we actually analyze the range of data sets over domain. Yeah, so there are lots of different ways of doing this. Again, we're trying to find what the best ISO values are for extracting the structures in a volume data set. The contour spectrum is really akin to contour trees, which I'll talk about next lecture. But again, it's really trying to determine what are the best isosurfaces. There's a paper from Hamish Carr on isosurface statistics and relevancy in, I believe, that's 97, very, very similar concept. And the other idea, besides sort of looking at the range of the data set, is to look at the derivative of the data at each voxel. And the idea here is that when we're specifying a sharp ramp or a peak in the 1D transfer function, what we're really interested in is this gradient or the surface that we're going to get out of it. And we want to make that surface match something that we see in the actual data set. So this is exactly what we're talking about. This is the gradient with respect to the scalar field. If you look at this as, you just take a central differencing scheme or forward differences, you would get a bunch of vectors out of this, and if you normalize them, you have some metric with respect to gradient. And so this is a way of approximating the surface normal of the isosurface. So really the surface normal at any arbitrary point in the data set. So I'm actually not going to go into that too much. The important thing is that when you start to look at the gradient magnitude, or rather inverse gradient magnitude, on 2 axes, so if you look at one axis of value and another axis of gradient magnitude, you actually end up seeing these sort of patterns that let us visually summarize the data set with respect to both range and gradient. And this is a very, very powerful tool, it turns out, in analyzing where the interesting boundaries are in especially medical data sets, but really all data sets. So this is changing the original classification scheme that we had from just classifying value to classifying simultaneously value and gradient magnitude. And what this is going to let us do is it's going to let us look at places where the value and gradient obey certain properties, and we're going to be able to classify that and pull out features directly with a little bit more work on our part. So if you, for example, had a 1D transfer function with a peak like this, and you looked at not just the value but also the gradient along this axis, this is what it would look like. But you can also, and you can actually constrict with respect to the gradient. And if you look at only regions where the gradient obeys certain properties, you can actually take out a lot of the lower portion of the tooth just by doing this. So all of a sudden you have a new tool for classifying regions of a medical or biological data set especially that you're not interested in, just because the boundary is small in some cases and large in other cases.
Why is the gradient so much lower for the lower part of the tooth?
Generally because you have fewer voxels in between, and you have a central differences filter or something like this, and the gradient is just smaller because of the values in the data. Oops. Okay, and you can actually do this and analyze entirely different features. So here we have sort of the we would have the low change in gradient magnitude values in blue and high change in gradient magnitude values in white. And using this, you're able to not just represent density of this data set, but also gradient. And you can sort of correct this to get out a really, really nice classification. And if you want to play with this, there's a tool called ImageVis 3D, and you can actually look at this tooth data set. These are all publicly available online, and play around with the 2D gradient magnitude classification here. There are a few widgets that let you sort of modify your transfer functions. So for example, you can select these portions of the 2D histogram that you're interested in. And you can move vertices around and add or remove features as you want. But it's more or less the same principle. And the idea again here is that these arcs in the 2D histogram are telling you where the interesting material boundaries are. And then you can, instead of color mapping just one scalar field, you can color map this sort of bivariate classification of the scalar field you're interested in and then its gradient magnitude. So this is, I think, coming out of Joe Niss's work in, I want to say, 2002 or 2003, where he was able to, yeah, Joe Niss and Gordon Kindleman, both of them worked on this data set heavily. In addition to classifying the dentine and enamel using gradient, they were also able to look at Hessian and the Jacobian to analyze curvature, so regions where you have more or less spiky features in the data set versus where you have sort of smooth, more kind of nice smooth surfaces. So high curvature would be sort of regions like this, where you see the dentine and pulp. A curvature-based transfer function would pick that out, and gradient is going to be more useful for things like the dentine and enamel. And I think this came out of Joe Niss's work, but he's showing that you can actually use fairly simple automated classifications based on gradient magnitude, even not using a complicated user interface like the one I just showed, to just get a better representation of boundary than you otherwise would. So the strengths of multidimensional transfer functions are You have better flexibility and specificity and higher quality visualizations as a result. The disadvantages are, well, they're based on the user interface. You can see it's a lot harder to manipulate that than it is to manipulate a 1D transfer function. Sometimes the relationships with boundaries can be unintuitive. I mean, it's very intuitive for this small medical data set, this tooth data set, for things like this CT head where you have a lot of noise and then you have boundaries of various width. It's also still pretty good, but there's some data sets, for example, cosmology, where you have incredibly high dynamic range, where these techniques are just not going to work. And if they do, they will need significant modification. So in short, multidimensional transfer functions are great, but the user interfaces are non-intuitive. That said, there was one user interface that Jonas came up with that was sort of a pick a region in the volume and reverse engineer the local transfer function based on this local value that you're interested in the domain. So you have this little widget here that you could use to kind of like a color picker almost, but here you're picking value, interest, and domain, and then you could map that to the widgets, similar to the widgets we saw in the Images 3D implementation, but you were actually picking in the domain to actually feed information into these widgets. So I think this was a very interesting concept that somehow still has not been reused a lot, but I think there's hope in techniques like these. And I mentioned the fact that you can use curvature as well as gradient magnitude to do a lot of this classification. And that's a way of actually doing the classification based on how sharp or fine a feature is and the geometric curvature of the underlying surface. Lastly, so that's really talking about univariate data, so single field data, and how you would look at the gradient of that single field to do classification. But there are extensions of this work or related work that deal with how to apply these techniques to multi-field data sets. And in multi-field visualization, it actually gets much more complicated because all of a sudden, well, first of all, you have more fields. And second of all, you don't really have any inherent relationship between the value of one field and the value of the other. Sometimes it exists, but you sort of have to figure that out on your own. So the best they could come up with back in 2003 was this sort of blobby multidimensional visualization where you manually placed Gaussian blobs in higher dimensional space, moved them around, and tried to get interesting combinations. But in short, we can render it, and we can render it accurately also, using a clever integration scheme using these error functions, but it's very hard to design good transfer functions for that. And in fact, that's actually, I think, one area where a lot of the isosurface literature, or especially the more recent fiber surface literature, starts to have an advantage over some of the, at least the older volume rendering literature. But there are also more recent, I'd say, InfoVis and DataVis driven methods for doing multidimensional classification. There's this work from Hanchi Go at PacificVis 2011 that is painting blobs on top of parallel coordinates. So annotating parallel coordinate plots and using that to do sort of course level classification of volume data sets. Similarly, there's Shusen Liu here in Utah has been working on multivariate volume visualization using subspace analysis of PCA plots. So instead of having a scatter plot matrix, you would have some projection that is sort of indicative of where the interesting regions of the scatter plot are in multidimensional range space. And you can kind of cluster them this way and use that clustering to color map the regions of interest in the volume. And the challenge, these are, I think, really, really great techniques and really where the research in this area is heading. But the challenge is that it's still very hard to get anything beyond a kind of high-level blobby approximation of what your data set is. So actually, I'll talk about that in the next lecture. The next lecture, I guess it's next Tuesday, I'll talk about isosurfaces and topology, which are sort of the indirect visualization equivalent of a lot of what we've talked about here in volume rendering. And then on December 1st, we'll talk about flow vector and tensor fields, so sort of advanced topics of visualization. Thanks, everyone, for your patience.